Welcome to today's talk. My name is Muthiah. I'm a software engineer in the data platform team at Airbnb. Today I'll be talking about writing production Flink jobs with our Airstream framework. This work was jointly developed with Hao Wang, who's not able to be here today because he's presenting at Kafka Summit in New York today also. Hao worked a little bit on it in the beginning, and I worked on most parts of it later in the game. So just a little bit about me. I've pretty much worked for the past about 10 years in data management space. The past 5 years more in the big data infrastructure world. Before Airbnb, I was at a startup, then at a ad technology company, Rocket Fuel, and before that I was at Microsoft SQL Server. So here's the agenda for today's talk. First, I'll start with the goal of the framework, Airstream framework, what we want to do, and then follow that with what is Airstream, basically high-level overview of the Airstream framework. Then we will dive into components that make up an Airstream pipeline. Follow that by, we'll put it together in a big architecture picture, and then we'll look into some of the use cases that we currently run in production. And after that, we'll do a deep dive into one such use case. Following that, we'll look at what the current and future plans for Airstream. And of course, we'll have Q&A at the end. So what's the goal of Airstream? We want to make authoring data pipelines easy for product engineers and data scientists. So it's not a technical goal necessarily. The focus is on making the usage of real-time data more widespread within the company. Basically, we want more product engineers and data scientists to be able to comfortably write pipelines and get them up and running quickly. We want to lower the barrier of entry for somebody to come and author a pipeline. Currently, an engineer needs to be familiar with data infrastructure, libraries, APIs, the whole ecosystem, in order to be able to comfortably write a pipeline in Scala or Java code. But how do we make it easier for people, product engineers especially, to leverage the real-time paradigm and easily write a pipeline without having to make deep investment into learning these technologies and all the infrastructure and the maintenance and all of that. So that's the exploration we tried with Airstream. So what is Airstream? It's a framework to define and execute data pipelines. The pipelines are created by stitching together a few building blocks. These building blocks are easily configurable and composable, and they can be instantiated mostly through configuration and chained together all in a configuration file. So essentially, the pipeline is created and defined through a configuration file. And the overall philosophy here is to make simple things easy and still allow complex things to be done within the framework. So why Flink? So Airstream as a concept can be supported in principle by multiple data processing engines. Why Flink? The main advantage obviously is the low latency streaming. Particularly, we have use cases where we need the real-time low latency, millisecond level latency support, and we also need support for high throughput. And frankly, no other data processing engine that we tried can support it. And also, Flink has very good integration with Kafka, which is used widely at Airbnb. And also exposes very easy to use high-level APIs. So this is definitely one of the attractions for using Flink. And on top of that, the full SQL support is critical to lower the barrier of entry, as we will look later. This support is pretty strong in the Flink framework, Flink engine. And of course, Flink is very well deployed. It's battle tested, it's stable, and it's widely adopted within the industry. And so all of this makes it an attractive ecosystem for us to leverage. So now we'll dive into what makes Airstream pipeline. So it's pretty simple conceptually. We have three types of building blocks, three classes of building blocks: sources, processes, and sinks. To define a pipeline, the author just has to pick and choose three components and use them based on the availability of data, and then configure them, stitch them together, and a pipeline can be created. Each of these blocks would have their own configuration requirement. For example, if you're reading a Kafka topic, then you just specify the topic name and some schema information about it, as we'll look later. If you're writing to a sink, you just provide a URL, and if you're writing to like a Redis, for example, you specify how you create a key and how you fetch the value from the data stream. And if it's a SQL statement, then you can just specify a SQL statement in the configuration file. So looking specifically at the sources, we have support for both structured and unstructured sources. Specifically, I want to pay attention to the structured source. What we mean here is where the framework can look into the schema of the data and be able to leverage that to execute the SQL logic. We'll look at it in more detail next. In addition to structured sources, users can obviously leverage any data source that essentially the framework treats opaquely. The user will then have to write custom code to be able to process that, but we still provide that plugin point for the user. And of course, we support dynamic data source such as stream source like Kafka, and also static data sets on HDFS or S3. And obviously, this comes directly from Flink's support. So Jitney source. So Jitney is basically a library developed within Airbnb that's used widely by all the the services and the applications. Jitney basically allows the application to define structured and versioned messages. The messages are defined in thrift format, and which provides the structure. And pretty much all services within Airbnb leverages this. So you can, if you look at the ecosystem of data floating through the real-time infrastructure within Airbnb, pretty much 99% of it is structured data that provides the schema. And so this is exactly what allows us to leverage we use the thrift schema of these messages to treat them as SQL schema and allow user to just simply write SQL statements to process and group and process this data. And the thrift format naturally translates into SQL format. So here in this example picture, we have a thrift class which corresponds to a message, and it has a bunch of fields. And essentially, each message then becomes a row, and each field then becomes a column. And all the types kind of translates naturally. The basic data types, as well as nested types, collections, all of that translates naturally into a SQL type system. So the next step in the pipelines after sources are processes. This process is basically the unit of logic. There are basically two classes really. One is SQL, which is the one that's more widely used. And then we also allow users to write custom UDFs in case they want to do something that's not expressible in SQL, or if they're actually using their own data format that's not Jitney. And so we are not really aware of the structure of the data that's flowing through the framework, in which case we allow the user to plug in their own code and to do their own processing. So looking more into the SQL process, continuing along the diagram that we saw earlier for the SQL source, the Jitney source, you can see naturally how the SQL can now simply be expressed over the thrift schema, really. So we have the fields, as we saw earlier, and the user just essentially treats the thrift schema as SQL schema and just directly writes the SQL statements. And this allows the user to do all kinds of projections, filtering, grouping, whatever logic they need to do in the real-time data pipeline. And that's what we try to depict with the example on the far right. In addition to SQL process, we have a UDF process. And this is for arbitrary logic, not expressible through SQL, as I said earlier. But we also see that it's used in cases where the pipeline owner wants to perform logic with side effects. For example, they implement a state machine that leverages some storage such as Redis, where the behavior of what the processing changes based on what messages were seen earlier. So in such scenarios where you have more complicated logic or more non-declarative logic that can be expressed in using a UDF. And also in the cases where the source is unstructured, there the option for the user to implement logic is basically to also plug in a UDF and then process the data the way they understand. And then final step in a pipeline is basically the sinks. And this is when there's a need to persist the pipeline output. The user can leverage one of the sinks that we have. We have a variety of sinks where the user can publish back the messages into Kafka topic in any format, or Jitney format, again use another Jitney thrift format and then publish the message as a Jitney message, or can write to HDFS. In one use case, we have a pipeline writing to a HTTP server for metrics, and we also support metric sinks that publishes to a metric system widely used within the company, which is Datadog. So I spoke about the components of the pipeline, what makes a pipeline. Now we can look at how a pipeline looks when you put it together. It may seem a little bit busy, but it's pretty straightforward. We start with the list of sources, data sources that the pipeline needs to leverage. Here you can see there are two. This is an abridged version of actual production configuration. Here we see that the pipeline depends on two event sources, which are essentially two Kafka topics. And it's Jitney in this case, and it provides just the Jitney class names. And this is what essentially allows us to look into the structure of the messages and give us the ability to execute arbitrary SQL on top of the structure. So then, following the list of sources, we have a list of processes. Processes are basically, as we saw earlier, either custom UDF or SQL logic. And here you can see that the SQL is written assuming the schema from the thrift message that's specified by the event class names here. And so you can see in this pipeline, they are doing a bunch of projections, formatting, and filtering. And you can see that the pipeline essentially follows, it assigns names to data sources and to outputs of processes. So in the process, you can see the from is tips would events, which is essentially one of the source. It's an abridged version, so we don't see the SQL accessing the search events part here. But basically, you can see how we just name data sets, data sources, name output of the processes, and thus stitch together the pipeline. And the second process takes the output of the first process and actually performs a side effect where it writes to Redis. And there's some bunch of configurations on how it has to be written. And finally, the sync in this example, there's no sync because the output is achieved, the persistence is achieved through the side effect. And so the sync is just a no-op sync, just pulls on the stream. This is all it takes for a user who's leveraging one of the Jitney event sources we have to write a pipeline and use that. So putting it together, if you look at what happens at runtime, the events are published by all our services and applications into Kafka using the Jitney format. And once a pipeline is defined in this configuration and deployed, the events are essentially fetched by the Flink pipeline. And we do the work to deserialize the thrift structured binary serialized messages into a SQL row. And then we feed that into Flink. We translate, obviously, the thrift type to the Flink SQL type. And then we deserialize the binary thrift message into SQL row. And then we feed all of that to Flink, and then the SQL statements, and then Flink will do the execution for us. This is the case of SQL process. And if it is actually a custom UDF, then we just, there is no, we don't do any of this work, and we just pass the binary message as it is, and we allow the user to perform whatever logic that they need to do. And this is how it's executed, and the data flows through the pipeline. It goes to the next process and the next sync and so on. So here's a kind of like a architecture diagram of how, what components are in play and how the events flow. Basically, user comes with a configuration file defining the pipeline, such as given in the example. The configuration file is parsed by our Airstream driver process. It will compile, essentially translate the configuration into a Flink job, and then it will submit it to our execution environment, which is either Yarn or EMR clusters in the future. And then that pipeline continues to run. It could read from any of the static or dynamic data sources we have, and it could be writing to any of the sinks. And this model of sources and sinks allows us to kind of provide a library essentially for people to write to a variety of systems within Airbnb. The ones that are common, open source ones I have listed here, but we also have a bunch of internal sinks which are internal storage systems. We also provide a sink, and then everybody can just leverage it and use it easily. So what are the benefits of this architecture? This provides, I think, the easy and fast pipeline development. And then of course we can reuse the sources and sinks. We don't need every single pipeline author to go and understand the same API code for the sources, Kafka, Jitney library, the sinks, Redis, Hive, and everything. And they can just essentially specify what the things that truly differ between each pipeline and the configuration. And we write the common code. And of course, as you saw, we leverage SQL heavily to make it easy for people to write the pipeline. And so we use that to make it easier for even product engineers who are not necessarily well-versed in all the APIs and systems to be able to come and author a pipeline quickly. And one very important benefit is that it shields the user from the underlying infrastructure and its changes. So if we, for example, change the underlying messaging system from Kafka to Kinesis, let's say, we just have to do the work once in our sink or source layer, and user's configuration remains unchanged. And we will just do the testing, and they don't need to worry about such changes. Otherwise, the user would have to go and change all their code. And this model of pluggable sources and sinks make it extensible, and for any future storage systems, data sources, or different types of logic, we can easily add one more source or sink or process, and we are able to continue to leverage this infrastructure. And so it's pretty extensible that way. So what are some of the use cases where we see the Airstream with Flink is used in Airbnb today? We have pipelines that are tracking user activity events on our applications and building real-time user profile. We have other use cases where essentially a real-time feedback loop is built into the product, because predominantly a lot of runtime events are published through Jitney and Kafka. Pretty much all the activity that's happening in the application is available to this infrastructure. So anybody can write a pipeline quickly, leveraging any of this data for their benefit and feed it back into the product. We'll look at one such example in the deep dive next. And there are a few fraud signal detection pipelines that really need the real-time latency, the low latency benefit of Flink. And so they leverage this framework. And we have a user device identity graph implementation that leverages Flink in a Lambda architecture way, where there's a real-time pipeline that's building approximate graph and that gets batch corrected at the end of the day. And we also have one use case where performance tracing traces, which are high in volume, that needs to be ingested into a separate metrics service is written using this framework. So we'll do a deep dive into one such use case. So this is a real-time merchandising profiler. Basically, this is a typical use case that leverages the Jitney formatted messages with SQL logic. Basically, if you look at the usage of Airbnb application, basically user goes through a journey from searching for accommodation or an experience to trying to narrow it down to what they want, and then finally making a booking, and then coming back later for the next experience and so on. So this pipeline essentially gathers the signals from the user throughout the journey of how they navigate, what pages they use, what they search for, and uses this in real time immediately and feeds it back to power subsequent experience of the user. So basically, if the user, for example, searches for a family stay, that event gets published by some application or service, and that feeds it into this pipeline, which essentially keeps track of all this information in a real-time profile store. And subsequent navigation, next pages of the application the user goes into, they just use this data to customize what they show. So specifically, in this use case, we are categorizing the user based on their activity in real time, and then subsequently personalize their experience from that point onwards. Yeah, so this was this was done in kind of like a watered down manner, trying to keep some state in URL parameters and cookies and so on. But now this allows like a full-fledged exploration of this kind of feedback loop, pretty much because any event that the service owner wants is available. Now they can leverage all of this data to kind of build like a very rich signal data, which then is leveraged to provide like a very customized experience for the user. So next, we look at, okay, what are some of the future work or current and future work that we are looking at? We have kind of made it pretty easy to onboard, technical people who are not necessarily well versed in the data infrastructure world to come and write a pipeline. But then now we have to follow up with support for maintaining the applications, so the pipelines. So one of the frequent asks is tooling to debug and troubleshoot issues. The pipeline, once the pipeline is running fine, it's great. But if there's a problem, and if there's specifically a problem in their logic, then they need to come to the data infrastructure, the offline world, and look at the logs and look at data. And currently, there could be struggle for people who are not familiar. And we are providing support, but we are looking at in what way we can provide tooling and interfaces for people to easily access these logs and troubleshoot the issues. Of course, testability of a data pipeline is always there. Data pipeline is not as easy to test as like an arbitrary piece of code. And so we are looking at what infrastructure we can provide for testability. And the other one key point is expose more streaming features. The way that I have described the pipeline being defined and used, I think it touches the surface of what is possible. So they're definitely using it, and we're seeing the benefit of it. But there's a lot more features to real-time processing. There's a lot of features that Flink provides. Complex event processing and many other features. And how do we expose this to the user for them to leverage it? So this is another question that we are kind of considering. So in summary, what have we gotten? So we have lowered the barrier of entry by leveraging structured data and SQL. We have allowed users to essentially define an entire pipeline through configuration and leverage the downstream output of that pipeline in their products or in their data science needs. We have decoupled the pipelines from the underlying physical infrastructure, which we are currently finding useful when we do certain physical migrations. And the model of lightweight constrained by specifying just sources, sinks, and processes allows us to make it pretty extensible. And we can continue to support new storages, new data sources, and new ways of new APIs. So that's the presentation portion of our work. Now I can take any questions.
Yeah, we definitely have time for some questions. Yeah, raise your hand. I'll give you the mic. Please wait for that.
Hi. I noticed that you're running your Flink cluster on AWS EMR. EMR is a great technology, but it comes with one major disadvantage, which is that it does not support multiple master EC2 nodes. So what I've seen when running Apache Spark jobs, for example, is that Amazon can decommission a node for any reason if it's undergoing maintenance or anything like that. How do you handle recovery from a cluster where the master node's taken out of commission if you have a low SLA?
So to clarify, we are moving overall within Airbnb. So today, all the Flink pipelines are running in Yarn, and we are looking at moving to EMR. I think that we are essentially waiting to see how the EMR HA turns out to be. And if that is good enough in practice, then that is one option. The other option that we haven't really explored yet is I think Amazon itself, AWS itself offers some sort of Flink service. And they have mentioned it briefly to us. We haven't explored it yet, but we have a few, we don't have too many of these real-time pipelines. At the tail end of this migration is where we are going to explore this and see how we are going to leverage what AWS provides. Yeah, right now we haven't hit that problem yet.
Do you address barrier for entry from infrastructure point of view? So if I'm writing, a configuration, I have my job, but I have basically no idea what is my infrastructure requirements. Do I need to do it separately, or do you address that under the same platform?
So we essentially provide users kind of consulting in terms of how to size their application, looking at what their QPS is and looking at what throughput they can achieve depending on what sinks they use. And according to their needs, we will kind of guide them on how much resources they would need. And from the infrastructure side, all these are parameters of Flink that we essentially also expose as part of the. So I guess one element that I didn't show is in addition to the configuration, we use Airflow which is a homegrown system for job scheduling and job definition. There you can essentially pass this configuration file and pass some of the infrastructure parameters like how many containers you want, how much memory you want, and things like that to size their application. And in terms of metrics, Datadog is widely used, and we have integration with Datadog. And for their pipelines, they can open and create dashboards and tap into the metrics to look at what's happening within their pipeline. And so that's the current level that we have for support for. And I think as the adoption grows, and depending on the use cases, if there are a lot of these low barrier use cases, then we'll look at more and more support for them.
Thanks.
You showed me the configuration. So how does somebody write that configuration? Is that a handwritten, or you provide some tool?
As of now, it's handwritten.
So how do you validate that?
So what we provide right now is, so since the space of what could go into the configuration is pretty dynamic, which depends on the sources and sinks and so on, we don't have yet a way, or I guess an automated way for validation yet. Essentially what we provide is a user can easily test a pipeline quickly in their local environment. They can tap into production data sources in a limited way, not reading all the volume, and they can essentially execute all their logic and write it to a CSV file or some other things like that. All those things are provided, and then user can validate their pipeline that way. And I guess, yeah, it depends on how the system grows and how the usage pattern, we can easily provide validation quickly. It's just something that we haven't gotten to yet.
Any more questions?
So you use Kafka all over the place, right? And assuming you have large volume of data coming in,
Right.
there's some failure scenarios when Kafka doesn't provide you consistency guarantees and ordering guarantees, some failure scenarios. And for you, missing any of this data is very important, right? So how do you deal with those scenarios with Kafka?
So right now we are just leveraging the support that Flink provides. Basically, the question is whether you have, there are some cases where the processing doesn't depend, it's a soft dependency, where if one or few events are missed, that's fine. This is kind of just to enrich the user experience. For example, a real-time personalization. In that case, there's no strong consistency requirement. But there are other use cases like the user activity profiler. We don't want to miss anything. And so we just leverage the support provided by Flink in terms of checkpointing to have at least once processing. We haven't had use case for exactly once yet. But that's how we ensure that. And there's certain level of retention in our Kafka cluster for like a few hours at least, and a couple days at least. And so we are able to not have any kind of downtime, actual downtime or actual data loss in our setup.
So you are saying like right now, you allow user to write a configuration and they can schedule a Flink pipeline by themselves. So what if like the job failed? Do you guys like have some like retry logic added to this this infrastructure, or like the user has to taken care of by themselves?
So it depends. For example, in one of the internal storage systems that we use as a sink, that has certain characteristics, certain exceptions that could come, and in that code we have already implemented the retry logic. And similarly for Kafka, I think we do have certain retry logic. And so at the framework level, whatever that we do naturally, we support to take care of these system transient issues like this. Overall, at for an entire data pipeline, I think the retry comes from the Airflow support, that the Airflow job can be configured in a way that even if the application dies, it can be restarted. And so we can set the number of retries. And so therefore, when this real-time job is deployed in production, combining the Airflow's retry support, internal retries that we have implemented in case-by-case basis, as well as the usage of checkpointing, allows us to kind of provide consistency guarantee.
And also, I think that configuration doesn't have like something like a watermark, this kind of stuff. So if I'm a user, I want to use this pipeline, do I need to have knowledge about all those like streaming concepts or contexts?
I think that we have kind of two classes of users, like product engineers who just want to leverage this jitney data and write some SQL logic, versus more serious use case like a user profile store where we are dealing with thousands of QPS and consistency. And depending on the use case, you would need to, like the more advanced users and more advanced scenarios, the user would have to understand more and more streaming concepts. But for those simple use cases, they don't need to get into that. And I think right now we don't have, I don't know if you said ML, but right now we don't really have like a direct ML use case. It's more of this like data processing, data pipelines, leveraging it for product use or building data sets.
Okay, thank you.
So I noticed you guys are writing to HDFS, right? So basically Flink is a streaming framework. So basically you're writing like the data really fast. Like that's like for Kafka you're writing data really fast. But for HDFS, the common problem writing to HDFS is that if you if you put the streaming a pipeline into HDFS, you will create a lot of small file problem. Basically, my question is for you is that how do you write to HDFS and how do you avoid the small file problem when you try to write the streaming data into HDFS with a low latency, assuming?
I think that, I don't know if, so that is there for like more like testing purposes, in case you want to get the data and look at it. I don't know if there's a production pipeline that's leveraging it, but regardless of that, I think the usual way that we control the rate of writing would be we have to see how parallel that your pipeline has to run and how much data it is processing. And I think the other way would be buffering versus potential data loss if the buffer is lost. And so those are the trade-offs that you have to consider. So we didn't have to look at that in our production setting yet.
Okay. So you guys using the Flink internal HDFS?
Right.
Okay.
Yeah.
All right, any other questions? Alrighty, thank you very much, Paula.
Thank you.